So cause and effect, the very first type of cause and effect is your classic X variable goes and produces a change in the Y variable. So there are 5 types of causation. That's the overall word we're going to use for all of these. But the first one is your classic cause and effect. It really only happens with physical processes. So maybe something like the more you train, like over a period of years, in basketball, your ability to be able to do a 2-point shot or a free throw. Where you definitely get it is with your true physics, physical processes, ice melting, temperature rising as a heat source increases, blood vessels dilating as they're exposed to caffeine, things that are just very clear. As the independent variable increases, the dependent variable changes either as an increase or a decrease. So don't jump to cause and effect because most things are correlations. Cause and effect only occurs when you can prove that the X variable actually changes the Y variable. Type 2 of causation is a common cause relationship. And this is the one that you will likely run into the most. It impacts a lot of the kind of data we deal with in school, where it is not one variable that changes, it is multiple things that can impact. So a common cause relationship means that an external factor actually causes the 2 variables to change in the same way. If you want to jot down a little note on this, when I think of common cause, I immediately think of 3 or more variables. And you can't have that on a graph, and that's why it causes some issues. So there's so many examples that I could give here. Guaranteed test question where I will give you 2 variables, and you will have to go and identify possible 3rd, 4th, 5th variables that are a common cause that impacts both. So for example, since I started teaching at the school, pizza sales at TD have doubled, and we also have a big increase in the number of buses that come to the school. And so, you know, buses, I think we have 11 or 12 buses now, used to be 6 or 7. Does pizza impact bus? There is a strong positive correlation between the 2, absolutely. Buses do not impact pizza, pizza does not impact buses. The common cause is a 3rd variable. Our student numbers have doubled. Okay, we used to be a school of around 200 students, we're now over 400. It's a very clear common cause relationship. And I would say that with a lot of your marks in EdSP, that would be the same too. Maybe there's a natural link that if you are good at functions, you might be good at data management, though that's not probably a strong relationship. But if you have really high marks in math and English or really low marks in math and English, and you have a positive correlation, in this case, it likely means that there's a common cause of general IQ, intelligence, how in grade 12 courses, a lot of what you do is based on how you write. So your writing skills, whether you're verbal intelligence, you know, visual learner, all those kind of things. So if you're naturally good at traditional school, have a high IQ, that's going to be the common cause. 3rd relationship of causation is reverse cause and effect. This one is a little trickier to understand. The key here is that there is cause and effect happening, but the dependent and independent variables, so your X and Y axis, are actually switched. The cause is the opposite of what you'd expect. And I hope you're thinking critically here, because as soon as I say the opposite of what you'd expect, well, it really depends what you expected in the first place. So I would better describe reverse cause and effect as a situation where you can switch the dependent and independent variables and kind of make an argument in both cases. So for example, there is a theory in a lot of studies that say watching TV causes depression. And the more TV you watch, the more depressed you get. But then counter studies were done that says, wait a second, is this actually reverse cause and effect? Are people who are naturally depressed, so clinically depressed, it's, you know, part of the mental health issues that they're dealing with, do they just naturally tend to watch more TV? Because if you are dealing with depression, you're less likely to go outside, be with other people, be able to work, and in that case, was the default going to be more just that you're watching TV? So that's what I tend to do with reverse cause and effect. Ask yourself the question, does watching TV cause depression, or does people that are depressed watch more TV? You hopefully looked at this link already. Very strange accidental relationships. There was a whole bunch of them that I posted last week where essentially there's two different graphs, and most of them were pretty morbid. It was very strange things like how much ice cream people ate or how much margarine was consumed in a province or state, and then comparing that to accidental deaths. So people that died in trampoline accidents or other strange things like that. Obviously, there's no direct link between those things. So how's it done? All you have to do is find two graphs that change at relatively the same rate. It can be linear or it could be a curve. Find two graphs that look the same, go and plot them against each other, and you're going to get a moderate to strong correlation. But there's absolutely no link between the variables. Accidental relationships. I had a student that went and graphed this once as an example. This was a number of years ago when Tim Hortons franchises were exploding across Canada, also when they moved Tim Hortons into the States. And there was a strong positive correlation over about a 10-year period of the increase in Tim Hortons locations and the US national debt. Completely unrelated. It just happened that they both were on a very steady positive increase. And as a result, there was a strong positive correlation. So the examples here are endless. Pick two graphs that look the same, do the R value between those two, and you will instantly have an accidental relationship if there's no logical link between the variables. The fifth one is a strange one, and it is, I have to put it in here, but it is kind of the more frustrating one to deal with. So I'm going to kind of give a couple of keywords here. With presumed relationship, you assume that there's cause and effect. So this one is most similar to cause and effect, where you say, yeah, X variable is going to impact the Y variable. But the key word here is that you're unable to prove it. It's impossible to show, to actually test, or it's unethical to go and test it. So this is a situation where you say, I believe it's cause and effect, but now I'm stuck. There's absolutely no way to prove it. It's very easy to prove cause and effect for a physical process. If you have something like how a temperature is increasing, or in physics, every single time distance speed relationship can be a very clear cause and effect, and those can be tested. But there's some variables where you see a strong correlation between them, but you cannot prove that the X variable actually impacts the Y. Why can you not prove it? Sometimes it's just that you're unable to, it's pointless. The example that I give here is a person's level of fitness and how many adventure or action movies that they watch. Where this falls apart and why it's presumed is that we know that watching TV does not make you fit. So why is it that people that have a higher level of fitness are more drawn to watching adventure or action movies? It's a positive correlation. There's a relationship there. It kind of makes sense, but it's almost impossible to test. What would you do? Go and put people in a situation where they have to watch adventure movies and then look at their fitness? A situation where you take that away and try to make people healthy or unhealthy, it just wouldn't work. So that's a bit of a weird example. The most famous one actually has to do with Alzheimer's disease, just a brutally sad degenerative brain disorder. We tend to think of it with grandparents more, but it does happen with other people too. And what has been discovered is that people that have had severe Alzheimer's, once they pass away and they do an autopsy of their brain, they find more concentrations of aluminum. And yes, aluminum is a metal. And we should not have aluminum or aluminum oxide in our brain at all. However, there are people that have Alzheimer's that do not have high concentrations of aluminum, and there's people with lots of aluminum that didn't have Alzheimer's symptoms or impacts. So what do you do with this? We know there's a correlation. We know that as aluminum concentration in the brain increases, the significance of Alzheimer's effects also increases, but we can't test it. Because how would you test it? You would have to get volunteers who would allow you to expose them to aluminum over a long time and see what it does to their brain. Completely unethical, completely illegal, won't be done. So that's an example where we're stuck with correlation. We know it's there. To me, the correlation is enough to be a concern. When I was in high school, almost all deodorants, antiperspirants had aluminum oxide in it. That ingredient has now been removed from almost all of them because you had a generation that was always applying that and putting a low level of aluminum in. When your parents were younger, they would have eaten out of aluminum bakeware, and we've replaced that with glass, with silicone, all that kind of stuff, so that you don't tend to go and cook out of an aluminum pot in the way that we used to. And all of that is linked to this correlation here. So those are the 5 types. Those are the ones you need to learn. Have the slideshow there when you do the quiz so that you can match it up to other situations. Some final things here. Extraneous variables. Extraneous just means extra or external variables. This comes into play with common cause for sure, but it can be a problem in other cause and effect too. In this case, when we have real life examples, we don't always have 2 variables. So the reality is that a correlation tests 2 variables at once. That's it. Equal to correl, first column of data, comma, second column of data, that's it. You can only test 2 at a time. So as a result, if I ask the question, your mark in this class is based on how much out of class work you do, your immediate reaction should be common cause. There is not one thing that impacts my math mark. There are many things. Then you list out all the extraneous variables. And there's so many other examples that we could look at. Go and pick 2 different things, anything to do with fitness, anything to do with health, mental health. You can't just pick one variable that tests it. So when you're actually doing correlation tests, you would go and pick a whole bunch of different independent variables, like how much you sleep, nutrition, how you naturally do at school, family impacts, all those kind of things. And then you would compare each of those to your math mark and see if there's stronger trends that exist. Once you have determined that there's a very strong correlation and you believe that it is cause and effect, the only true way to prove cause and effect is to do an experiment. And this now goes back to the scientific method, which you had to learn when you were in science. And to do a true test, if there is causation, you set up an experiment where you have 2 groups, your experimental group and the control group. Control group, everything is controlled. So everything's similar. Experimental group, you go and change just the one independent variable for that group. So for example, if you were doing a test on caffeine, you would control everything. Everyone in both the experimental group and the control group would have to sleep about the same amount, have the same diet, live in the same kind of situation, similar job, similar age, all those kind of things. And then you would do the experiment of the independent variable being caffeine. And so those people would have strict amounts of coffee or energy drinks or other caffeinated beverages that they would have to consume throughout the day. And your cold control group would have 0 caffeine. So no chocolate, nothing else that contains caffeine. And then you've done the experiment because everything else is controlled. Any changes that you see are a direct result of the independent variable, which in this case was caffeine. So that's the final thing. Any difference in the results with the 2 groups is because of the change in the independent variable. You're now done. You can prove cause and effect. This is, of course, is a huge process, lots of experiments, lots of money and time that go into it. And that is why so many people just use correlation, because immediately something that you can do on the on a spreadsheet is just looked after for you. So that's your only true way to test for cause and effect. Everything else is just correlation, and that's why we spend so much time on correlation.